look at optimization problems. These are the type of problems where a farmer has a certain amount of fencing and they want to make a rectangular plot, and you've got to find the maximum. You did these in Algebra 2 with quadratics and a couple with polynomials with our calculator, but today we're going to be looking at these problems from a calculus approach. So the first step in any of these problems is to carefully read the problem. You might even want to read the problem twice. And then once we've done that, we need to identify what quantity we're optimizing, what do we want the most possible out of, and what do we want to constrain, what's our constraining factors. So, a farmer has 2,400 feet of fencing and wants to fence off a rectangular field for Bessie the cow that borders a straight river. Since Bessie the cow is the smartest cow and won't drown, the farmer decides he will not fence along the river. What are the dimensions of the field that has the largest area? This should sound really familiar from Algebra 2. So we have our river, and then we have our fencing. It goes along those two sides. And again, we don't know this side or this side, but we do know that we have 2,400 feet of fencing. That is what's constraining this problem. If I call this side width for a moment, we'll have 2x plus the width has to equal that 2,400 because the max area would definitely use all the fencing available. And so width is 2,400 minus 2x. So I go back to my picture, say goodbye width. We'll have 2,400 minus 2x. Now I want to find my area. Area of x is equal to x times 2,400 minus 2x. Simplify. 400x minus 2x squared. That equals area. Now, again, if we were doing this from an Algebra 2 approach, we would find the vertex there, maybe using negative b over 2a. But we're not, so we want to use calculus. Now, I know the maximum of this quadratic is going to occur at a point where the derivative is equal to 0. So let's find the derivative. A prime of x is equal to 2,400 minus 4x. We're going to, again, because maximums occur where the derivative is 0 or undefined, there's no value that would make this derivative undefined. So we're going to start with this. 4x is 2,400. 4, x is 600 feet. That means this is 600 feet, and then this side is 1,200 feet. So my dimensions are 600 feet by 1,200 feet. Basically, anytime we see one of these problems, we're going to start by understanding it. So we need to read it, we need to figure out what's known, what are the given quantities, what's optimizing, and what's constraining. Then we're going to introduce a diagram if needed, some notation, A for area, for example, or like I did on the last problem, V for volume, H for height, the quantity that we want to minimize or maximize in terms of anything else. So in the last problem, I wanted to maximize area, so it was really important that I found A of x, and then I took the derivative of it. And our quantity could also be minimized as well. And then if q of x has been expressed as a function of more than one variable, then we might need to use our information to eliminate other variables. So, a cylindrical can is made to hold 1 liter of oil. 1 liter of oil, that's the same as 1,000 cubic centimeters. Find dimensions that will minimize the cost of the metal to manufacture the can. Well, the metal on the can, that's the same as the surface area. So surface area on a can or a cylinder is 2 pi r squared plus 2 pi r h. Two variables. Well, we knew it was coming because I warned about it in our last set of steps. But we can do this. We're going to be eliminating here. And as I look at this, I've got r squared, r, and h. It's probably going to be easiest to get rid of that h because it's only in one location. The other thing I know is that the volume is pi r squared h. So, and I know that I want 1,000 cubic centimeters for my volume. So I can say 1,000 equals pi r squared h. And then if I want to isolate h is equal to 1,000 over pi r squared. So I'm going to rewrite my surface area equation with now having h eliminated. What this is doing is it's making my surface area, instead of just having it as S, I'm going to have it S of R, okay? Because I have my surface area as a function of just R. My pi's are canceling here, and I'm just getting R. This should have been R squared. Whoops. It's a negative one. Okay. So now, because I have it just in one variable, I'm going to take the derivative. Remember, our maximums or minimums are going to occur at values where either the derivative is undefined or zero. So now I'm going to get a common denominator. It's easier to see where the zeros would be if it's all in one fraction. So 4 pi r cubed minus 2,000 over r squared. Now, values that would make this undefined would be r equaling 0, so that's a critical number. And then I would also want the critical numbers for the numerator being 0. 4 pi r cubed minus 2,000 equaling 0. 4 pi r cubed is 2,000 divided by 4 pi. R cubed is 500 over pi. And then the cube root on both sides. So r is equal to the cube root 500 over pi. So our critical numbers are either this r equals 0 or r equals the cube root of 500 divided by pi. We're going to eliminate r equals 0 because that means there's no can. And while that would give us a very small surface area, it would also not hold the volume we're looking for. Next thing I'm going to do is find out what h must have been. Well, I know h is 1,000 over pi r squared. Now I'm going to rewrite r for a minute as 500 pi to the 1/3. And when I square that, that'll be 500 over pi to the 2/3. Well, that just looks delightful. We don't like to have fractions in our fractions, and while we don't have to simplify a lot on the AP exam, that's kind of just a big no-no. So I'm going to multiply by 500 over pi to the 1/3. I know, it looks like I'm making it worse, not better. Just wait. It's going to be awesome in a moment. So that ends up with 1,000 times this over pi 500 over pi. Well, these pi's can cancel. And then 1,000 over 500, well, that's just 2 times 500 over pi to the 1/3. So our height is equal to twice the radius, or our height and diameter are equal. Or, if you were wondering, that radius is about 5.419-ish. Okay? Centimeters. Cool, huh? So far, though, on all of these problems, I've just kind of taken the critical values. I haven't tested to make sure it really was the absolute max. Mostly because they've only had one. So, but if c is a critical number of a continuous function defined on an interval, if f prime of c is greater than 0 for all x less than c, and the derivative of x is less than 0, it's negative for all x greater than c, then f of c has to be an absolute max. That's just saying that it was larger on everything. And similarly, you can say a similar thing for being an absolute minimum. Okay? So, hey, same problem again. That same cylindrical can. But now, let's try it with implicit differentiation, right? Because I had two variables. That means I probably could use it. Just scooch it up a little bit so I have some more space. Okay? So, again, we had s is equal to 2 pi r squared plus 2 pi r h. And I also had 1,000, because I'm plugging in the value. That did not change. Okay. So I'm going to find the derivative implicitly. So s is equal to 4 pi r plus 2 pi h, because I have to do the product rule here. Treat this as one piece and that's the other. So we're doing the derivative with respect to r. 2 pi times h plus 2 pi r h prime. Okay, this is x prime. Okay, and on this one, derivative of that is 0. Again, I have to do the product rule. So we'll get 2 pi r h plus pi r squared h prime. Okay. So I want to minimize the surface area, so we'll make this 0. I'm also going to divide by 2 pi, because pi's are just making things look unnecessarily complicated. So we'll have 2r plus h plus rh prime. Okay. That looks a little better. And then on this one, I'm also going to divide by pi. Now, 0 equals 2rh plus r squared h prime. Now, I'm going to do something that most of the time we don't do, and I'm going to divide by r. Now, follow me for a minute. We can't divide by a variable usually because we don't want to divide by 0. But if I have a radius of 0, that means there's no can and then there's no math problem. So, I'm going to divide by r. 0 is 2h plus rh prime. Ooh, rh prime. That sounds so familiar. Like maybe it's a system of equations. Like that. Look at that. I'm going to subtract these. Boom, boom, boom. And I will be left with 0 equals 2r minus h. So 2r is equal to h. The diameter and the height have to be equal. Boom. Got the same answer. But I used implicit differentiation instead. One more problem for today, and that is to find the point on a parabola y squared equals 2x that is closest to the point 1, 4. Y squared equals 2x. I'm going to rewrite that as x equals 1/2 y squared. Why? Because I don't want to deal with radicals. Okay? So I'm writing mine in terms of x. That means a generic point on this parabola would be 1/2 y squared, comma y. Yep. I'm going backwards, but again, this is a sideways parabola. There's nothing here that says I have to do it as a function. Now, the distance, using the distance formula, is the square root of 1/2 y squared minus 1 squared plus y minus 4 squared. Not digging the square root because it's going to be really tough to take the derivative of, so I'm going to square both sides. Now, if I'm trying to minimize the distance, the minimum of the distance squared will also have the same value as the minimum of d. Because think about the smallest number in d. When you square that, it's still be the smallest number in that set of squares. So, kind of a tricky thing. So now I'm going to rewrite this as f of y for a moment. And now I'm going to take the derivative of this. I'm going to use the chain rule rather than multiply that out. I could have, though, if I wanted. To the first times y, chain rule. Don't get screwed up by it. Times 1. So now I have 2y, 1/2 y squared minus 1 plus that. I'm going to distribute. I get y cubed minus 2y plus 2y minus 8. These two cancel. I get y cubed minus 8. Now that looks like it has the potential for 3 answers, but we know by our difference of cubes, this will factor to y minus 2, y squared plus 2y plus 4. Again, by our Algebra 2 knowledge, we know this piece only has I guys in its answer, so I'm not going to bother even solving it. So y minus 2 equals 0, so y is equal to 2. That's the only real solution from that cubic. So if y is 2, way back up here, 1/2 y squared is going to also be 2. So the point on that parabola that's closest is 2, 2. And that concludes this lesson.